Hello, welcome to this video. This is 4-1 and today we are going to interpret derivatives in context. This whole unit, Unit 4, is all going to be about contextual problems, real-world application problems where we are using derivatives in context. So let's go ahead and dive in. Alright, here we have a graph of f of x, and it says the graph of f of x is above along with the line tangent to f through the point 1, 0. And they say it is known that f prime of 1 is equal to 3. Interpret the meaning of the statement f prime of 1 is equal to 3. Well, what this just means is it means at the x value, so at x equals 1, at x equals 1, f of x has a slope of 3. That is the instantaneous rate of change of f at 3, okay? And you could even be appropriate there to say instantaneous rate of change. So we've been studying these derivatives, including different differentiation rules and the meaning of a derivative graphically. However, we have always been working without context. We've been looking at just a table of values or a graph or a function in symbolic form. But now what we're going to do is we're going to apply that to real-world meaning. And these functions have real-world context. So the derivative is also going to be interpreted and used in that real-world context. And here we have some appropriate notes, things to pay attention to specifically in this unit and these problems today. So in real-world context, we rarely use x and y since they don't have context. The variables often correspond with the situation, and most often we use t as our independent axis, our x-axis. So it'll be, I guess, a t-axis now. Important note number 2, in contextual problems, derivatives have units. So pay attention to whatever your units are. Units of y being divided by units of x. You constantly want to make sure you're getting your units right, as well as you're using your units to inform you. Important note number 3, in real-world context, a derivative is a rate. So the slope is the same thing as a rate, okay? The slope is a rate, or when they say a rate, that's the slope. And then lastly, derivatives are still instantaneous. It occurs at a specific point in time. Okay, if you could almost like freeze frame or take a snapshot at that moment. So it's often important to describe when rates are happening, okay, at t equals 3 minutes. Here's a table of values of some things derivatives are, what they mean, and what they are not. Derivatives are rates. Okay, so that just means the rate of whatever it's talking about, and it's not the total, the amount, or an average. It's the rate. It's the rate of how something is changing. Derivatives are instantaneous. They occur at a specific moment in time. It's not an interval of time, so it's never from 2 to 7. It's a specific value. And lastly, they are contextual with units, so make sure you're paying attention to your units again. And it's not the units of the original function, because remember you're taking a rate, units of y divided by units of x. All right, so let's go ahead and look at an example, and some of these should seem familiar. We kind of touched on these in Unit 2 when we were approximating derivatives, but here we have some context. So example number 1. The height of a sunflower in inches is measured over the course of 7 weeks. Use the table above in order to estimate h prime of 2. Include units of measure. Okay, so if I want to go ahead and estimate h prime, over the course of 7 weeks, of 2, I'm going to go ahead and approximate this. So h prime of 2, and I'm just going to look at my table of values. So where is 2 at 2 weeks, h prime of 2? Well, that would occur between 1 and 3. So I'm going to go ahead and I'm going to use the values. I'm going to take the function value h of 3, I'm going to subtract h of 1, and I'm going to divide by 3 minus 1. So this is just average rate of change, right? And we've done this a million times. 25 minus 7 over 3 minus 1, which is 2. So this gives us 18 over 2, which is 9. Now it's important, you're going to want to include the units of measure, include your units. So our change in our y values in our numerator, that's in inches, that's the height. 9 inches is how much the sunflower has grown. And then over the course of, well, we reduced, so it's going to be 1 week. So 9 inches per week. Okay, and it's important, remember, that is just at 2 weeks. So specifically at 2 weeks, it's growing 9 inches per week. Here's example number 2. The number of cars entering a parking lot of a grocery store T hours after it opens, that's important, T hours after it opens, is changing at a rate modeled by the function C prime of t. Okay, so here they're giving us a derivative where C prime of t is measured in cars per hour. Use the table above to approximate C double prime and include units of measure. So I want C double prime of 6. C double prime of 6. Well, in order to figure out that rate, I'm just going to use average rate of change for the table given. So if I want that rate, I'm going to take the rate of cars per hour, okay, and I'm going to divide by t hours. So I got to find my points. Well, C of 6, okay, that's smack dab between 5 and 7. So I'm going to use those values. So we have C prime of C prime of 7 minus C prime of 5 divided by 7 minus 5. So this is 54 minus 92 over 2. Okay, and we get negative 38 divided by 2. That's not negative 38. That would be, oh yeah, that's negative 38. Negative 38 divided by 2, which gives us negative 17, negative 19. Okay, and I'm going to include units. So cars, this is cars per week. That is the y values, right? Sorry, cars per hour. Whew. Cars per hour, and I am dividing by the units of my independent variable, which is hours. So this is cars per hour, and you'll often see it written as negative 19 cars per hour squared. Okay, so that's our second derivative, negative 19 cars per hour, or per hour squared. Okay, and then the negative. I mean, think about that contextually. What does that mean? We're going to go ahead and talk about that now. So the second half of this lesson is interpreting a derivative in context. And make sure you include the following. Make sure you include the context. Don't just name the function. Talk about what the function is modeling with words. Units. Do not forget the units of both what the answer is and the x variable. Often it's time. Be very, very clear. If it's instantaneous rate of time, talk about that moment at t equals, state it. And then rate, include the word rate in your sentence. Okay, include that rate in your sentence. All right. So right here it says interpret the meaning of your answer in context from example 1 above. And I really wish there wasn't the cut here. I want you to go ahead and do that here. So you may have to go on to the next page if you're looking at the notes. But here is kind of a sentence frame for interpreting a derivative in context. Okay, so they say here the blank. So what's f of t in context? Or what were we talking about in example 1? Well, that was the height of the sunflower. So the height of the sunflower is it increasing or decreasing? Remember, this is a rate, so is that rate increasing or decreasing? Well, if I go up here, it's a positive number. It has 9 more inches per week. Well, that's increasing, right? You can think about a plant or a sunflower plant growing. That's increasing. It is increasing. Increasing. When would it be decreasing? Well, here we have a negative answer. I have negative 19 cars per hour per hour. So the rate of cars leaving the parking lot is decreasing. Okay, so a negative answer indicates decreasing. Okay, and then at a rate of, and then whatever f prime of c is in units, and use the absolute value. So if it's negative, do not include a negative, just indicate what that value is. So, and this was inches per week. Per week at what time? At t equals, well, we were looking at 2 weeks. At t equals 2 weeks. Okay, so that's our sentence frame, and those are the kind of the structure that we're going to be writing these problems when we're interpreting a derivative in context. Okay, let's go ahead and look at example number 4. A factory produces delicious cans of corn. For the typical corn enthusiast. One particular machine is notorious for packaging cans of corn at impressive speeds. The amount of cans that this machine has packaged after t seconds, so the amount of cans this machine has packaged after t seconds is modeled by the differentiable function c of t. Part 1, it says approximate c prime of t. Then, using correct units, interpret the meaning of the value of this value in context of the problem. Okay, so c prime of 1, I'm going to go ahead and approximate this with the 2 closest points, so 0 and 2. Okay, so this is approximately 52 minus 16 divided by 2 minus 0. So this gives us 6, so 36 divided by 2, which is equal to 18. And I want to include units in this. So this is 18. Our y units are cans. Our x units or t units here is seconds. So cans per second. Now we want to go ahead and we want to, using the correct units, interpret the meaning of this value in context of the problem. So again, if you need that sentence frame, it's right above us, but we're going to go ahead and we're going to interpret this answer. All right, so what are we talking about? C prime of 1 means, and what is the function? Means the amount of cans packaged. And what is it doing? Is it increasing? Is it decreasing? Well, packaged is increasing. It's a positive number. Increasing at a rate of, make sure you include that word, rate, at a rate of 18 cans per second. 18 cans per second at t equals 1 second. Okay, and there you have it. That is our interpretation in context. All right, so let's go ahead and look at another example in context and see how else they can ask this type of question on the AP exam. At the end of a football game, fans begin to exit the stadium. For 0 to 40, the number of fans that have exited the stadium after t minutes can be modeled by the function f of t. Okay, here they say find f prime of 8. Well, I don't know about you, but that function looks really, really nasty. Okay, you could compute that by hand, but my guess is with that type of function, this is going to be a calculator active problem, and we're going to go ahead and utilize our calculator. So here I am at my calculator. If you don't have yours, please pause me and retrieve your calculator and do this along with me. Okay, so I'm going to go ahead and I'm going to add a calculator. And one thing with these rate problems on the AP exam is they'll often want you to go ahead and use it multiple times, use a function. So I recommend to my students to go ahead and go into Actions and define the function. So Menu, Actions, Define, and I'll just call this f of t is equal to, and I'll go ahead and enter this function. So we had 50,000, okay, and 1 plus 535 e to the power of negative 0.29 t. And actually I'm going to use x. I don't like using t. Sometimes the calculator gets funny with other variables. So I'll use x, okay, and it says done. So now I want the derivative. We want to find the derivative at 8. So f prime of 8. So I'm going to go ahead and go into Menu, Calculus, Derivative at a point. Okay, variable here, I guess if I had a different variable, if I called it t, I would use t, but my value is 8, and I want the first derivative. So I hit OK, and then the calculator just inputs this structure for us. So now it's saying the derivative of what with respect to x? Well, I need f of x. That's my function that I want to differentiate, and notice it's at x equals 8. If I did not define it, you would just enter that function here in that space. So you don't always have to define it, especially if you're just using it once, but that's my recommendation to practice inputting and defining certain functions that you'll use multiple times. So we go ahead and enter this, and we get f prime of 8. I'm just going to jot this down if you want to make a note of this. F prime of 8 is equal to 265.590. Okay. Found it. Using correct units, interpret the meaning of this value in context of the problem, okay? So, I need to go ahead and say here, f prime of 8 means, what does that mean? What are we talking about? Well, we're talking about fans exiting the stadium. It means the number of fans exiting the stadium is increasing at a rate of 265.590 fans per minute. So remember, we're looking at our units here. So f of t, that's in fans, that's people, and then our independent variable is t minutes. So fans per minute, okay, at t equals 8 minutes. All right, and there's our context. Awesome. Okay, so that's with a function, and then lastly here we have a graph, and they say here for 0 to t is less than 10, the rate of people are getting on an escalator in people per second is modeled by the function p, where t is measured in seconds. Okay, so they say use the graph of p to find p prime of 8, and then using correct units, interpret the meaning of this in context of the problem. Okay, so first thing, I need to find p prime of 8. P prime of 8. All right, well, here is 8, and I'm going to look up here, and it looks like the slope here, looks like we're dropping 1, and we are running 2, so negative 1/2. This is equal to negative 1/2. Okay, found it. Now I need to go ahead and interpret the meaning in the context of problems. So p prime of 8 means the rate that people are getting on an escalator okay, and again, I'm just pulling this directly from the problem. The rate people are getting on an escalator, okay, is, and what's happening? Is it increasing or is it decreasing? Well, it's a negative answer. Is decreasing at a rate of, and here I'm just going to use the absolute value, so 1/2. And what are our units? Well, remember, it's very, very important, especially if you have a graph. Here they say the rate is people per second. So here we have people per second. People per second. Okay, and then after t seconds. So this is actually people per second per second. So 1/2 people per second per second. So I guess I could say people per second squared. Okay. At t equals 8 seconds. Okay. Again, for the units, you could have said people per second per second. You could have said it that way, or people per second per second. But I think this looks cleaner, honestly. Okay. All right. Hey, that's going to do it for this video. We have interpreted context, or we have interpreted derivatives in context, interpreted rates. Okay. Give me a thumbs up, like this video, subscribe for more awesome math videos. Catch you next time. Peace.